Alright, here's how we plan to start this thing off. I'm going to do a review of some of the older games, including the one that we're going to use as a project game. This is just to give you a highly opinionated view of the older games from someone who's either worked on or owned most of these things. Let's start with Freedom. 1976-77 was produced both as an electromechanical and solid state, and it was their first attempt at a solid state game, and has a lot of tryout features on it that they found weren't going to work, and they did a lot of changes between this and the next game. The next game being Knight Rider. This is our project game. Shown here is another electromechanical. They produced more electromechanicals of this one than they did solid state. They were still trying it out. Guys were scared of it. But it was starting to catch on. They sold a total of over 10,000 of this game. It was very popular. Evel Knievel was another one that was a winner. This one is shown as solid state. This was made both ways also. The first one that was totally solid state was 8-Ball. Probably the best of all of the early ones in my opinion. This couldn't have been made electromechanical because it had memory from player to player, from ball to ball, and it would have been a gigantic task to try to do this with electromechanical relays. And over here, the trader Bobby Orr, when he's no longer in the Bruins uniform, it was a nice little game, but it was more or less a standard Bally playfield layout. What I mean by that is they seemed to like 3 or 4 thumper bumpers, a couple of drop targets, and the standard package entrance at top and bottom. So they were pretty much same old, with very few exceptions. This is a very attractive game, and actually a nice playing game because it's got a nice loop shot feature up around here and a big saucer. These are really tough to find with anything left on the playfield, but it's a nice game to own. Blackjack isn't. This was one of their first of a bunch of dogs. Now this was made electromechanical much earlier, and then they brought it back out again as though they were running out of ideas. Again, they featured the memory and recall, strikes and spares. Okay game, a little different feature. It had lots of rollovers on the playfield, which got dirty and quit working very soon. This is the first game. All these other ones up until now have been chime games. This is the first game with sounds. They came out with another MPU with another dress line on it, and they were able to utilize a package of electronic sounds. So this is probably one of the prettiest games ever. The artwork on these games was phenomenal. There is not much of anything going on the playfield. I don't know if we can get a good shot of that or not. Not much of anything happening there, but really a good looking game. $6 Million Man, its main feature was 6 players rather than the standard 4. Nice playing game, not bad at all. In nice condition, this is a good game to own. The 6-player feature was used just once, never again. Didn't make any sense anyway because most people can't keep track of who's up next when you're playing 4 players. 6 players just made it that much harder. This game has got more hype than any other Bally game. For my money, it's probably one of the prettiest art-wise. Good-looking game, but definitely no better playing than $6 Million Man or any other early Bally game with a standard format. 3 thumper bumpers, a set of drops, a set of stand-ups, and the sounds, if anything, are a little annoying. I don't know why they couldn't do better with the soundboard they had, but some of these games are really annoying to listen to. This is a nice little laid out playfield. I had one of these recently that was absolutely beautiful. It was in nice shape. And it's a good playing Bally game. Okay to own. Star Trek is kind of a groupie piece. The people who want it because it's Star Trek, not because it's a Bally pinball game. And there isn't much to look at on here because they've got a street photo shot here, fast action shot. But the playfield is laid out a little bit different than your standard Bally, but not that much different. And there's a shot of the playfield there. Okay, here a little different layout, but again, pretty much standard Bally. Now there's an exception. I don't care what group is on the playfield or what the tie-in was with the group. This is an outstanding playing game. This has got 4 thumper bumpers, drops, symmetrically laid out playfield, a fast-acting game, a cluster of lights to fill up, a grid of lights to fill up in here. It's just a nice playing game. I rate this up there with 8-Ball as far as play appeal is concerned. Now we come to a wide body. This particular one is Paragon. Again, a dynamite looking game with great artwork. But wide bodies, in my opinion, are too sluggish. They just don't have any action side to side. They're just too much area to cover. And although this was inventive, it came with the first one with inline drop target. And 4 thumper bumpers and 3 flippers and whatever else. They threw everything with the kitchen sink in there. Pretty game. Not bad sounds, but not much going on. Harlem Globetrotters, interesting little piece. A couple of new features on the play field. More inline drops. Once they got them, they never stopped using them. Dolly Parton, I like this game for one reason. You can buy these real cheap and they're great for parts. Other than that, nothing there. Future Spa, another wide body. They sold a few Paragons, so they said, why not? So this is another good game for parts, but no other reason to own it, in my opinion. Ground Shaker, a remake of an electromechanical game called Twin Win, which is actually a better game. This has an annoying sound package in it and pretty much standard Valley playfield layout. Sorry guys that own that one. There's a playfield layout right there. In the original electromechanical, they had a spinner in the center of the playfield. It was a 2-player game, laid out pretty much like this here. It seemed to be more fun to play than this one. Kind of a classic here, Silver Ball Mania, probably one of the best backglasses ever. If you're going to collect a backglass, you don't have to go any farther than this one. Better than Playboy. Dynamite looking, mirrored backglass. Don't have anything except this little burper on Space Invaders, but it's a wide body version of Silver Ball Mania and slower. And I'm not too thrilled with any of wide body, so we'll just move right on. Rolling Stones had a tie-in with a group, but also had a pretty good playfield layout. Not too bad. It's worth owning, but again, most people who own this want it because it's Rolling Stone tie-in, not because it's a pinball machine. This one I never owned and never even seen. This thing came and went so fast, it was amazing. I've never even seen one, so I can't comment on it. It's got an interesting playfield, lots of drop targets, but pretty standard Valley fare. Here we go again with another wide body. Let's try it again. This time it's called Hot Doggin', and I think they got part of the name right anyway. Alright, an attractive game. Okay, let's move on to a really nice looking game here, Viking. Nice interesting playfield, good artwork, nice one to own. Kind of hard to find with anything left on the playfield, but interesting little game. Over here, Skateball. This came out around the same time as Flash, has pretty much the same playfield layout with the ball crossing over the top, lots of drop targets, good playing game, and the first of the 7 digits games. And over here to Frontier. This was a nice laid out playfield. You've got some inline drops, you've got a grid to fill up, a light grid to fill up. Interesting sound effects on this game out of the same board that they've been doing nothing with them till now. And pretty game. Not too many of them made, kind of hard to find. And of course the classic Xenon, what can I say? This was the one that really turned it around for Pinball and for Belle. No ifs, ands, or buts about that one. Flash Gordon, a major disappointment as far as I'm concerned. It was their first attempt at a 2-level game. I mean, they were trying to stay up with Williams and Black Knight, and this thing was just a dog. Not as bad as the movie, but very close. And of course, the classic 8-Ball Deluxe. It's never been done better as far as pool games are concerned. This one was made 3 different times. I'll show you 2 of them. The third one we could never find any release on. As late as 1985, they were still making this game. Just about a classic. And there's the classic playfield layout. You can see those white thumper bumper caps only came on the very first games. Kind of hard to find those. Fireball 2, a major disappointment of a remake of the Fireball game. Instead of a spinner down here, they had this little ball roll back and forth that made a very annoying sound. And this is speech, multi-ball, everything you could possibly want in a game, but it just didn't have it. This one, however, did. This was a great game. Fathom. Multi-ball, speech, nice playfield layout. One of the longest shots in pinball. All the way up here, around the top, all the way here, into the corner pocket. Just a nice game. Interesting concept here with Medusa. Probably the most overloaded game ever made. Mini playfield up here, programmed drop targets, another playfield down the bottom. Good action, interesting game. It's worth owning. Another classic, Centaur. The artwork on this is worth having the game for. There's a 5-ball multi-ball with a unique fire system down below that spit the ball out up this ramp after you earn certain things on the playfield. Tough to find in good condition, but classic, no doubt. Electra, 3-level playfield. I mean, Gottlieb was making them, why shouldn't we? Not even worth talking about. There it is there in all its splendid glory. Good for parts though. Multi-ball, speech. I'm not even sure it was multi-ball. Doesn't matter. Over here we have Vector. This is overkill at its best. This is a 2-level playfield multi-ball speech. Drop targets left, right, top, bottom, everywhere. This thing was one of the most overloaded games ever made. And tough to get running, tough to keep running, but fun to play. If you can get one in really nice shape, get it. If it's a dog, don't even bother. Okay, rapid fire. Gun game. Less said about that, the better. Okay, Pac-Man pinball. Here we go again. We can't get the players to play pinball, so why don't we make it a half pinball, half video game. It wasn't either one. And Spectrum. Just some colored drop targets, no thumper bumpers on there, not much action, just a strange game. They didn't sell very many of them, so people want them for that reason. Interesting 2-player game with a plastic playfield, speakeasy, good-looking old-style cabinet. Nice little game to own. Usually you can find them in pretty good shape. Second time around for 8-ball deluxe. And now we get into the, wish we hadn't gotten the pinball business. Why don't we cut back on costs, do away with multi-ball and speech, and see if we can make some nice cheap games. And here we go. Gold ball. X's and O's. Kings of Steel. This one isn't too bad. Black Pyramid. Spy Hunter. And the god-awful Fireball Classic, which wasn't anywhere near as good as the original Electromechanical, which I didn't like either. This is desperate times here, folks. We're trying to stay alive. Here we got 8-ball champ. Nobody's buying pinball now. This is the middle of the video era. Nobody's buying this stuff. And last but not least, or maybe it is least, Cybernaut. This is when they finally decided to give it up. They scrapped the old system. Even though this one is a remake of the old board system, it's kind of unique. It's got a special board in it, but they finally gave up on it and they went into a whole new production line. We won't bother covering any of these, but covered such illustrious names as Lady, Luck, Strange Science, God, Motor Dome, Black Belt. These are mostly forgettable. All right, let's go look at some literature now, and let's get started on this thing. Okay, let's take a look at some of the publications you're going to need for this. This book is typical of the ones that came in the game. This is a little later version of the same thing. This is one you had to send away for, but it's really important if you can get a hold of a copy. Theory of operation. Also nice to have if you can find them. It's the parts catalog. It covers all the special stuff on your game. Most important of all, you need a nice clean set of schematics. Now they don't even have to be from the game that you're working on. Any set out of any Bally game will work for what we're going to do. Now we're going to take a look at some of the special tools and ordinary tools that you're going to need also. You really can't get any more basic than these, but you're going to need them just the same. It's your standard pliers set, good set of cutters, decent set of screwdrivers, nut drivers of course, assortment of open-end wrenches, set of sockets if you want, good cutting tools, and you'd really be lost without this. That's a combination drill and screwdriver. Now we'll take a look at some of the electronic tools you're going to need. Okay, let's start with this solder station. This isn't really totally necessary, but if you're going to get into any kind of board work at all, you're going to want something that you can adjust the temperature on, get greater control on what you're doing, and this really is the only way to go. But if you don't want to spend 100 to 150, then just move on down to this Radio Shack beauty here for under $10. And it'll do the job. You just can't be in a hurry, and you've got to spend a lot more time on setup. Now let's move on over to meters. This is another Radio Shack item. They're on sale all the time for $20 and less, and they'll do just about everything that we've got to do in this series. This particular one has got a diode check function on it, which is definitely something you're going to need, so look for that when you go to pick out whatever one you decide to get. This is considered close to the top of the line. This is over $100, and it won't do much more than the Radio Shack item, but it is far more accurate, and you can believe the readings you get out of this one. Now this little item that you can't make out all too well right here, that's called the Logic Probe. This came from Radio Shack 2 for under $20. We'll show you how we use this. It isn't a mandatory tool, but if you're going to do any kind of work at all on the MPU, you're really going to need one of these. It's every bit as important as a good meter. And next to that you'll see just some test leads that we make up any size, any length you want, with some alligator clips on the end, and these are going to come in handy also. Now let's get over there and find out what's wrong with the game. Okay. All right, here we go. 1976 Belle. Ooh, Knight Rider. Oh boy, this is really something. Both electromechanical and solid state. Surprisingly, they sold 4,000 electromechanicals and 7,000 solid state. This was a winner for Belle anyway. Well, let's take a look inside and see what we got. Yipes. It's like stepping into a time capsule. Everything is original in here, best I can tell. Original lamp driver, original MPU, with quite a bit of battery acid damage. We've cut the battery out of it as soon as it came in here. That'll be one of the things we'll be covering. We'll be repairing that. Looks like the original solenoid driver board. At least it's old enough to be. So far I can't see any real reason why it shouldn't run. Oop. Here we go. There's the original power supply. And they've got the main line disconnected for some reason or other. I think probably that's where we'll start looking. In the meantime, the overall appearance, with the exception of a little rust here and there, not too bad. Back glass is nice. Play feels surprisingly good. Probably died before it had a chance to get ruined. A little bit of wear up there. We'll be doing a touch-up on that. Now let's take a look at the play field underneath. Okay, we've turned it upside down so we can get a little better look here without too much trouble. And actually it's not really that bad. Everything looks pretty original. It hasn't been hacked up by too many people over the years. The only thing we've seen that's been changed on it so far is a couple of coils here, and the flippers have been changed, and some of the typical terrible wiring done by most of the operators during the 70s before they were really comfortable with these electronic games. And I also noticed they got a cap stuck across the out-hole switch here. I'll explain the problem they had with that and how they ended up curing it. So, it looks like we got a fairly good start here, and this should be interesting. I think we've pretty well decided that this is the problem with the game, but what we're going to go ahead and do is reconnect that connection that was left off, and we fired it up, and you're supposed to get a series of flashes on the MPU on this LED that's located right down there in the bottom. We got nothing. No flicker, no flash, nothing. So what we do in a case like this, if you've got an extra set of boards, it really makes it easy. What we'll do is just substitute a known good MPU in place of this one and see what response we got. Well, we've done that, and still no flicker, no flash, nothing. So we're going to go ahead and assume that what we got a problem with right here, we've got no power coming out of this A2 power board. So what we're going to do now is do some voltage checks right on here where they have the test points. And we've completed that phase also, and we find out that we're missing, or as low actually, voltage required by this power supply up here to give us our 5 volts. So now we're going to go ahead and yank the transformer out of there, find out where the voltage disappeared to. So that's the next step. Well, let's take a look at the schematics now. This is where we're going to get most of our information for troubleshooting. I've circled the section that we're interested in now because we've lost 5 volts to the MPU. Usually when that LED on there doesn't light up or flicker or flash, you've lost logic power, which is the 5 volts. It originates down here in this section on the transformer, as shown on the schematic. You've got a bridge rectifier there taking about 12 or 13 volts off the transformer, rectifying it down and making it 11.9, which then heads directly from there on into the voltage regulator. Well, we finally found out what the problem was with our game here. Very simply, this transformer with its secondary windings, like those 2 white wires there in the center, we checked those out with our trusty VOM and found out that it's less than 6 volts coming out. So we must have a bad winding in the transformer. Everything else checks out good on the board. Bridge rectifier, the rest of the circuits are okay. So we're going to have to scrap this transformer and start in with another one. But that's probably a good thing to do anyway. I'll show you why. This early style transformer and power assembly mounted in the cabinet like this right here, straight up in the air up against the back box. And everything and anything that could fall off of the inside of the game, including screws, nuts, bolts, is going to land right on top of that board. Someone has already made some repairs on there. You can see a couple of unorthodox jumpers that are on top there that someone has had to replace because something probably fell on there and shorted one of the rectifiers out the ground and just burnt some traces. So they just went ahead and jumped it in and patched it up as best as possible. So we're going to go ahead and get rid of this one. They only use this in 2 games anyway, Freedom and this Knight Rider. Then they realized that this configuration wasn't going to work. So they scrapped it. And they went to this style right here. This is pretty much what they stayed with only minor variations up until 1980. So we got 76 to 1980 covered with this. And this is pretty much straightforward. The schematic that we showed you before works with this one as well as the late one. So we're going ahead and stop now and substitute this known good device we robbed out of another game. And we're going to go ahead and put it in there and see what the next step is in troubleshooting. Okay, we're back. And what we've done now is installed that later model transformer assembly, which is actually kind of a tight squeeze due to the door design on this early game. Fits okay, you gotta move some wires around, but we added a piece of fish paper on the front because the door comes awful close to it when it's closed. But it'll work out okay. And since then we've fired it up one more time and found out that we are getting a flicker and 1 flash out of the MPU, and then it's stone cold dead. So we've got no choice but to start right in on this MPU. I know we're going to have to do extensive work on it to clean up the battery acid, but there are other problems in it because it never got that far in the test. So we're going to go ahead and set up and get ready to do quite a bit of work on this and other MPUs. Try to bring you along slow and careful and show you just what that test will do for you and what it won't do for you. Now let's get set up. What we're trying to do now is take a little closer look at the board that come out of the game we're working on. Down here at the bottom, we're going to take a look at the damage done by the battery. What happens is these NiCad batteries are left in there for years and years. These guys put these games away in storage, and the battery was alright then, so they figured it'd be alright 5 years from now. Well, it isn't. It busts open at the bottom on the inside and the seams, and the battery acid starts following the copper traces. This particular one right here, it has eaten away the bottom row of pins on the socket down there at the bottom. It's worked its way over to the left, eaten away some of the connections, and you can see a pretty good size lump down there in the corner. This is all battery acid damage in through here, and all of that is going to have to be cleaned up because it's nothing but one continuous short from one end to the other. We'll have to take some time out here and do all of this rather than eat up time doing it for you. We'll explain to you what we did and if we accomplished anything. Not all of these boards can be saved. If the damage hasn't been too extensive, like I know that socket right there is gone because the bottom row of pins is bad, but the flash is telling me that the socket above it is bad too. Now whether it's a bad socket or a bad connection, I don't know, but we're going to do all of this stuff and then attempt to get this board to work before we give up on it. Let me show you what some of them look like that should be thrown away. Here's one here that we had to give up on. Now this is pretty extensive damage, but it had continued along throughout this entire circuit up through here, along here. We replaced the socket, didn't help, and the damage extended over into this area up in here. So probably this socket too was damaged, but by then we'd spent about three hours on it, and it's time to quit. There is a time when you just have to say stop, so We couldn't get this one to fire up. The damage was too extensive. We replaced almost every single one of these components you see in this area right here have been replaced. But they're not all failures. Here's one that we use as a spare. This one came out really nice. We were able to replace some of the components in this area. We replaced this socket here. This one's original. And cleaned up this whole bottom area down here. We don't install a battery back in it until we're ready to use it. You don't need the battery in there to get the game to run. It's only in there for memory, for scores, etc. So this is a success story. But the problem is, we'll get the original board back here. It isn't just so much replacing the parts. What happens is that the corrosion builds up on the copper traces. And if you don't take it off completely, you can't solder on there. That acts as an insulator, and there's just no way you can do any kind of soldering. You can apply as much heat as you want, and it's not going to go anywhere. It acts like an insulator. So until we get every bit of this crap off of here, and keep cleaning it and cleaning it, find out just the extent of the damage, we're not going to know if we're going to be successful. We'll flip the board over and take a look at the bottom. The bottom is alright. It's clean enough to be able to get at there to get that socket out, at least hopefully. And that's what it's all about. If you can get in there and get it clean enough to be able to do any kind of component replacement, then you're going to be able to be successful. Let's go ahead and start. We're about the halfway point right now. What we've managed to do is scrape a lot of the stuff off, get down to some good copper. It's starting to look a little better, but you can really see the damage on that socket now. Those pins just fell apart as soon as we took the top of the socket off. Over here on the right, you'll see a bunch of holes along there, and it seems like there's an awful lot of them. The reason for that is they weren't sure what kind of a battery was going to be available when the game came out, so they left plenty of holes in there for all different size, lengths, and styles of batteries. But the only important connections there are here are this one over here, which connects directly to that resistor. That's the positive side. If you connect the battery here, you got a jumper on the bottom. It has to end up over here. Well, these three connections are your positive end, any one of those three, depending on the battery you use. Over here, these two are ground, and that's ground. And there's even another one over here. I don't know whether they can plan on using a car battery or what, but when you flip this over, you can see that those aren't all connected together. So it's up to you to make sure that the ground ends up where it's supposed to and that the positive side ends up where it's supposed to with jumpers. And now we're about to do the hard part. I'm going to try to set up as best I can and show you how to remove this socket. I may have to do it in bits and pieces because it's hard to work around this camera and be able to get the information across at the same time. We'll give it a try. Alright, as we're getting ready to set up here for doing some soldering, removal, I want to show you a couple of the tools that we use here for cleaning the board. This one really works out nice. Got a wire bristle in the end. You can slow the speed down, get inside tiny places with it, tight places. Does a nice job. The tool we use, of course, for taking the big chunks out and for picking in around the areas is this one here. And whenever you can get in there, you can use a little bit of sandpaper along the edge of the traces where there's plenty of room. But when it comes time for the actual desoldering, you've got to have some kind of a tool like this here. This is a Radio Shack item, and it's okay. But you have to load it. Pretty hard to load with one hand. You got to load it with two. It's a little awkward to use, but if that's all you can find, then it'll do the job. You're just going to take a lot more time. This is the one that we like. This a little more expensive, got a lot more power, but you can reset it by pushing up against something with one hand. So we'll be using this tool here. Now what we're going to do now is try to get set up so you can see how some of this is going to go. We hope to be able to get at least one row done with a tight camera shot. And then you get a pretty good idea of what it takes to get this stuff off of here. Alright, we're ready to give this thing a try. Now the important thing is you've got to be able to apply just enough heat to get the solder liquid, not too much, or you're going to melt that trace right off of that PC board. You can see the change in color on the solder when it liquefies. That's when you want to move in. You're going to get some spatter all over the place. Don't worry about that. You can pick that up later on. The fewer number of trips you have to make on each pin, the better. These aren't designed to take a whole lot of hits. I'll work my way down this line here. You can see those pins are starting to pull up out of there now, some of them are. They might be loose enough when we get done to yank them out. If not, we'll have to go to the back side and do that row over again. That one didn't want to take. I think we probably got some dirt on that one. There you go. And one more here on the end. That one's a little dirty too. There it goes. Alright. Now what I want to show you, I'm going to go ahead and finish that thing up, and then I'm going to go back and show you how you can check what you've done up until now. See whether or not you need to do some more work. Okay, at this point we've used the desoldering tool on the top row, turned it over, repeated the operation on the bottom. The pins have a tendency to want to come out through the top, especially if you've used some clippers like I did to cut them off close to the board. This fattens them up a little and won't let them drop down through, so they'll have to come back up to the top. What I've done now is put a light, I've backlit it with a neon light, so you can see that she should be pretty clear before you attempt to put the socket in there. I can move that around a little bit. You can see all of the eyelets are opened up. Now we've lost the bottom half of one of the eyelets, and about the fifth one in the bottom row. But that's okay, because that'll still catch. There's enough left so when we drop some solder on there, that should run right up on that trace. The problem you're going to run into is when you put the socket in there, you've got to put just the right amount of solder on it. If you keep shoving solder down in and around the pin, it'll take it and it'll run it all the way back up inside the socket, and you'll never be able to insert the chip. So you've got to put just the right amount on and use a very, very thin, fine solder. Now the importance of keeping this clean can't be emphasized enough, because if this wasn't perfectly clean, that solder is going to sit there and bubble, and it's not going to go down that trace. You can see what the battery acid damage has done right here. If you take a look at that line running down to ground off the bottom of the socket, right there, that's busted loose. Battery acid did that. And here. Plus, over here, it stops short of that capacitor. So those are two places we're going to have to pick up on after we get the socket in there. I'll make a note of it so I don't forget it. Now another thing I'm going to do is, when I get done, I'm going to run the ohm meter across all of my leads to make sure, in fact, that this pin is connected to this trace through here. And any other one that I suspect might be a problem. This one connects the back 2 row of pins. I'll make sure that they ohm out across. You really should do this before you fire it up. You're just trying to check up on your work. What I do is I get an old PC board that I have stripped out with no sockets or anything on it, and I use that as a template of sorts and make sure that if it ohms out on the other board, it should ohm out on this one. You got to do a little bit of troubleshooting when you get done. Normally when you do a socket, you don't have all of these problems because you don't have all of the battery acid to contend with. So a changeover is much, much easier. This is about as extreme as it gets, about as hard as it gets. Another point. Alright, one final thing on this before we move on. When you're using all of these tools down there to do this cleanup, you're going to find that you might be knocking some of the components loose or even cracking them or breaking them. You almost can't help it because it's pretty tight down in here. But for the most part, everything you see in this area, once you've checked it out with your schematic to find out what the ratings are on them, most of this stuff is obtainable from Radio Shack. So if you bust a component, it's not really a big deal. You're just going to have to make a note that you're going to have to replace that piece before you can expect this thing to start again. Now we're going to move on to the next section, which will be trying to show you how to solder that socket in as neatly as possible. You might want to, if you can, again, it's a luxury, I know, but if you can find a couple of old PC boards they're getting ready to throw out, you should be practicing on one of those before you get into this heavy stuff, because it does take a little time to learn all of this and a little bit of practice. Let's get set up for some soldering now. Alright, let's give this a try. Like I said, what you've got to remember is you're not trying to load that thing up too much, but you should be able to read it. When you start putting solder down inside the pin there, you should pull it through to the other side, and you can judge pretty well. Can you get that one going? Here we go. What's enough? Too much is still too much. Here we have a double trace, so we can start right in the middle. There you go. There's another double trace coming up. 2 pins connected to the same pad. You can see that bubbling. That usually means it's heated up enough for it to follow the pin back to the other side. If you don't make contact with the other side, first of all you got to determine that it needs to be, because not all of them go through both sides. What you're going to have to do is, that's where your ohm tracing comes in. Now, this wire I'm using, solder I'm using, is a really good quality, a little expensive, but very, very nice solder. The stuff you buy from Radio Shack is okay quality, it'll do the job. But this stuff seems to really tackle the impossible. They're really tough to get at places. Okay, we're going to call it quits on that top row. And I'll finish it up and then come back. I want to know what to show you on this is when you first insert that socket, you're going to bend a couple of these pins over, usually the ones in the corner, to hold that socket from falling away from the PC board on the other side. Doesn't matter whether there's a gap in there or not, it just makes a nice, neat appearance and a little better job if everything is seated the way it's supposed to. Now I'm going to ahead and finish this up and then come back and check out some other things. Alright, now we're back again after we've finished up on that socket down there. Only to find out that we got some additional problems with this board. Couldn't get it to run at all. Still having some startup problems. So we looked around a little bit more to find out what else might be happening. And we discovered that someone had taken this chip right here and actually soldered it into the socket in the corners, probably trying to keep it from vibrating loose or whatever they were trying to do. So we had to clean that up, pull that out, and put a new socket in there. That made it a little better, but it still was having problems trying to start. So we decided to just stop and back up and do a whole procedure that we go through sometimes when we have an in-doubt board. That's a board that we find in the game that maybe the guy threw in there that didn't even belong in the game. It didn't have the right chips. It didn't have the right anything. So we started from scratch and took out this stuff one at a time and inserted them in a known good board to verify that they in fact work, which they did. But then we noticed that up here on the top, someone had been doing some work on the processor socket. Let me get that a little clearer. So this socket is sticking up about 1/8 of an inch off of the board. And the guy actually got in there and with his little soldering iron and soldered the legs down to the top of the board. Maybe he figured he couldn't get the solder to follow through from the other side or whatever he was trying to figure. This thing is actually up 1/8 of an inch. So we did some readings off of this, but we found it actually was all right. We suspected that he was having a problem putting it in there, and maybe that's what our problem was, but it wasn't. And we finally found it after about a half an hour of messing around. I'll show you what we came up with. It's a good thing you didn't have to sit there and watch us do it, because it took, as I say, about a half an hour. Get that focused in a little better. What we found was that there was another bad trace here. Even though this one looked all right here, appeared to be okay, it wasn't. So what we did was, on the other side of the board, we put a jumper from that pin there on down to the other end. You can barely see where the pin was. Well, that took care of it. Then she started. And as far as we can see, I think we're going to be all right with this board. That was just attributed more to battery acid damage than anything else. Now you can see that we've also put a little tiny string of solder right in there to take care of that gap that we showed you before. Then over here we put a piece of copper trace. Actually, that's solder wick. It comes in a roll. It's about 1/8 of an inch wide, made of braided fine copper wire. We put that in from there on down and underneath here. That took care of the ground. That's the actual ground for this chip right here. So then when we strung our other jumper in across the top for the 5 volts, we had to put an insulator on that to make sure that we aren't going to come in contact between that 5 volts and the ground. And on the other side over here, we got this cleaned up as best we could, and we've run the solder across there. So our two connections are now going to be right here and right over there for the battery. But let's discuss what this LED was trying to show us when we were trying to get this thing running. All we were getting out of it was a flicker and sometimes a flash. Well, the sometimes a flash, not every time, was this damn chip that they had soldered in to a flaky socket. The reason why they soldered it in is this. These sockets that they had weren't very good. They lasted for a couple of years and then they gave troubles. Now, let's see if I can get this top half of this one up here. I'll show you what the first cure was. Everybody tried this first. They thought this would be the answer to it. This thing has like a cover on it. If you take the cover off, it exposes the row of pins. Once we focus it will. Now when you put the socket in there, you can go farther into the pins than it did before. So that seemed to cure the problem, but eventually these pins began to, these socket grooves here began to wear, and the pin would sit in there and maybe make contact and maybe not. So these are kind of lousy. So anytime we suspect that we got a socket problem, there's no other cure for it other than to put a nice firm new style socket in there, something that takes some real insertion power to put the chip in. There really is no other way around it. You could mess with these sockets, the thing will run, it won't run, it'll shut off in the middle of a game, it comes back down to these sockets all the time. Now as far as the flashes are concerned, let me explain something about it, if I can. We'll back up on this thing here, see if we can get a little bit of picture of what we got. Now, this particular diagram here comes from Stearns, and it's a really nice piece of work, and we're going to insert it in with all of the different charts and everything we're going to include with the game. with this tape rather. And what that tells you is basically what the test program is doing. Now we'll start with the processor right up here. Okay. Now what they're trying to tell you is that this first flicker is your 6800 MPU. And that first little flicker, it runs itself a bunch of tests in and around this particular processor chip. You got 2 clocks, you've got address, you've got reset, VMA, which is a valid memory address, interrupt request, data lines, and a read and write. All of this has to be up and running, or it won't even do that little flicker. If it just comes on and stays on without the flicker, then probably you've got a problem, something to do with the processor. But it really could be anything connected to the processor also. It doesn't have to be just the processor. So there's a lot of tests that have to be done to determine that. Basically, there's about 5 different voltages that you can look for on this processor chip. The most important ones are these 2 clock signals, pin 3 and 37. In the book that comes with every one of these games, they will list out all of the possible things that could be wrong on that flicker. And they emphasize this clock on pin 3, pin 37, what the voltage should be, and a reset line, and these others. They're all listed in the book there. And if you run through those tests and everything comes up pretty close to what they're asking for voltages, you can just about rule out this as being the problem. Chances are you've got a trace bad someplace and it isn't getting address or data lines correct. So you can suspect this chip at first, and you can go ahead and replace it with a known good one, but I think you're going to find out to be much more involved. It usually is. It's more difficult to get this 6800 up and running properly than anything else. But a lot of guys give up. They never get any farther than that right there. If you're lucky enough to get it to flicker, but no first flash, then you can look down here and you can see flash number 1, anything from U2 to U6. Okay, that's your personality chips right here. U1, U2, 3, 4, 5, and 6. Not very many games use any more than 2. Occasionally you'll see 3. The only one that ever used 5 was the very first game, Freedom, and that probably stands by itself for a lot of reasons. It's the chips are special, everything's special on that. It's kind of tough to do any work on. But then they went to 2 memory chips, and then eventually just 1 in this U2 position. The U6 is probably a utility ROM, I guess is the best description, and that's where your instructions come for the test, and a lot of other instructions for the game, for the particular game. But they can use this same chip over and over again. This thing was used from Knight Rider all the way up to Blackjack, probably 5 or 6 games with the same number, 720-20. Remember before we showed you on the bottom of the playfield in the outhole switch, someone had added in a capacitor. Well, what he was trying to do was get the thing to read the ball being in that outhole switch. Some of these games, these early games, the ball would sit there and not kick back out again for the next player or the next ball, whatever. The reason for that is it was a glitch in the program. Right down here on this 720-20. It doesn't usually show up on every single game, but it shows up quite a bit on 8-ball. It showed up quite a bit on some of the earlier games, those are the chimes. And the cure for it is very simple. You find yourself a new U6 with 720-21 part number. You're not going to find it in any Bally Parts book, but they were given out as a correction ROM to all of the dealers, and they're out there. You just simply have to find them. And if you're having a problem with the early game, this is the answer to it. You find that 720-21, this is a 20 here, and put it in there, and that solves all of the missing ball doesn't kick out, how come the game stopped problems that you have with the early games. Now, if you've gone by the first flash and you come up on the second one, we work our way down the line, and that'd be U7 if there is no second flash. That's this one right here. This is a 6810, and it's very easy just to pop that one right out of there. Let's see if I can get it in the picture. There she is right there. Now that's the second flash. The third flash, if it doesn't show up, is the next one down the line. That's a 5101 CMOS RAM. It's a bookkeeping RAM. Read and write. Scratch sheet. Whatever you want to call it. This one is a frequent failure. So if you get all the way up to 2 flashes and no third, you can almost be positive that it's that chip right there. Again, there's any one of the things that could around it that could cause it. Any loss of information going in and out of this. All of these talk to each other. Each one has to be ohmed out. If you have a major problem with one of these boards, you'd have to go from a certain pin on this one to the top, on down the line. A pin here is connected to the pin here, and so forth. And if these things aren't all connected and talking to each other, then it will simply shut the game down. Okay, that takes care of the third flash. Now the fourth flash is, let's see if we can get this thing zeroed in here. Okay. Fourth flash is, there we go, what they call a PIA. This PIA and the one underneath it are both identical. You can see the two of them together in that shot. This PIA and this PIA. Okay, so flash 4 would be flash 5 rather, I'm sorry, flash 5 would be, flash 4 is the U10, flash 5 is the U11. Now you can easily swap these around. If this doesn't come up, you can swap this one for this one and see if you can get it to go one more flash. But these are fairly inexpensive. You can buy these today at a lot of electronic parts houses for $1, a couple of bucks for this chip up here. None of the chips on here are all expensive except the personality chips. Now that'll get us through the PIA, which is not a common problem, but they do go. So now you're up to flash 6. Now flash 7 is actually centers around a U14 over here, but this is kind of complicated in that it's what is called a zero crossing circuit. Very simply, if you've lost the 43 volts for some other reason, say the fuse blew after the last time you played the game or during the last game, you shut the game off and turn it back on, she'll go 6 flashes and no 7th if you don't have the 43 volts coming off the transformer. The same 43 volts that goes to the playfield has to come here for what they call a zero crossing detector. And that U14 is part of that circuit. Most of the time replacing the fuse will cure the problem, unless you've got a problem with this chip itself. So what I'm going to try to do now is set up and show how you can make yourself, without a whole lot of expense, a comparator circuit. We're going to rip out a wiring harness out of a cabinet of an old Belle game, just the part in the head, not very elaborate. That, a transformer, a voltage regulator, solenoid driver, and an MPU is all you need to make up a fixture, and you'll be able to fire up 2 boards simultaneously right next to each other. And one will be a known good board. You should always have one of those around. And then you can go ahead and take your comparison voltages from one off the other as they're sitting next to each other with the use of a logic probe in the volt ohm meter. This is really the best way to test out a board that you're having a problem with. It doesn't fall under the normal group of problems that you have. So we're going to go ahead now and build this little circuit and show you how easy it is, just using parts that are available without spending a whole lot of money. And you'll end up with a nice little test fixture that you'll be able to do a lot more board work with. Okay, let me see if I can explain this as simple as possible. What I've done here is I've made up a plug, you can see right here, with an inline shutoff. This is just an ordinary plug off any old drill or motor or whatever. Oh, you can go buy one. And I've robbed a connector off of another game and put 3 wires into this J2 connector up here. That's AC in AC out, and ground. I'm able to power this up right now. It's just turning that switch on, connected up to an extension. That enables me, off this bottom connector, to power up this solenoid driver voltage regulator. Alright? Well, this wiring harness that you see right here came out of a game, out of the head. Nothing's been done to it. This is just the way it is. The only thing that's special that's here so far is this line cord that I made up. This is how I test transformers and this PC board right here out of the game. I take the transformer out of the game, hook this connector up to it on the bench over there, and do all my readings and everything else, where it's much easier working than it is climbing up inside of a cabinet. Okay, so now we've got voltage regulation here. Goes on over through the cable and connects right down here on J4. This is the only connection needed to power up the MPU. Now there's a lot of extra wires on here that aren't needed to power it up, but I just left them in there rather than clip them out of the cable. And up here you see a junction of 4 more wires added on. Those are just robbed out of another wire harness, and they go down here and connect up to the bottom board. Now I've got 2 MPUs off the same power supply, off the same solenoid driver, off the same transformer, getting ready to be powered up at the same time by the solenoid driver. So we'll turn it on, and I think you can make out the LED flashing on the top one and on the bottom one. Okay, now both those boards are up and running. They don't necessarily have to be good boards. That's not the purpose behind this. What we do is this bottom board would be the one that's not working. Now it might only flash once, the LED might be on all the time, doesn't matter. This one will take off. It's a good board up here. It'll take off and it'll do its test and it'll start, irregardless of what this one down here is doing. One board will not drag the other one down. Now this is where I make my comparator test now with my logic probe. You hook it up to the 2 power terminals on the MPU board. You've got a ground on the bottom and rather 5 volts on the bottom, and the ground at the top. This thing is powered by 5 volts. And now I want to make my cross checks. I'm having a problem with this board here, and I suspect it's in the one of these data lines or address lines. So what I would do is go down the line here and make a check on the known good board on a particular pin, see what kind of a reading I get, and then go back down here and check this out. If the reading isn't exactly the same, then I'm suspect of either that line or that chip. Now this might seem kind of involved, but actually you wouldn't be doing it on every single pin all over the board. You would have by then zeroed in on what section you think it is. And this little tool, to me, it's a lot faster than using a VOM, which can be kind of bulky to hook up. If you get a difference in signal, then you go to your VOM and find out what the difference is. Whether you got a low voltage, is something pulling the voltage down? Is it absent completely? Is it got a pulse online it's not supposed to have? This combined with the VOM will give you all the information you need. That and the schematic. Now let's cover that schematic one more time. This is probably the most confusing page that there is, especially if you're just starting out and you're trying to figure out what all of this stuff is. See if I can move in on that a little bit better. Now, the way the schematic is laid out has got absolutely nothing to do with the way the board is laid out. The schematic is laid out like most schematics. They start with the power usually coming in on the left-hand side. Here's your power input here. Then for convenience of the architect who does the drawing here, the engineer, he'd put a circuit that's directly related to that in that corner, right near there. It's got nothing to do with the position of the actual connector on the board. This is a matter of convenience, so he cuts down on the number of traces that he has to signify here. Otherwise this would be such a mess you wouldn't be able to figure the thing out at all. So a lot of this simply drops a bunch of lines drop off into one, which really is confusing if you're thinking that they're all going to end up on one trace. Well, they aren't. These are all independent lines, but because they're all address and data lines, they all share the same information going to the same chip. So it's not necessary to show 16 or 20 or whatever individual lines coming out of here. Only when it is necessary, like these individual lines. Now you'll find that these connections on here are the critical ones that you need to get this processor to run. So a lot of this significant information is put on here on one side where you can see it. Also, you'll see that the pinout is not necessarily the way it is in the game. The pinout starts on a large chip or any chip. It starts with 1 here in this corner, proceeds on down, in this case down to 20, then 21 on the other side all the way back up to 40. But in this one here, they've got them jumbled up. You got a 10 and a 12 and a 9 and whatever. What they're doing there is a matter of convenience again. This has got nothing to do with what you're actually seeing on there. So you can't confuse yourself by trying to look at this and then look at the chip on the board and wonder why there's difference. Then they've got some of the other circuits isolated. Your clock circuit over here is isolated. There's a lot of troubleshooting done on that frequently. You got a zero crossing circuit up in here, which is isolated. And this is just a matter of convenience to be able to read this thing. It would be pretty hard to read otherwise. Then you go on over to the right-hand side, and you got your exits. This is where all your switch inputs and stuff are coming in over here. Your information for your displays, solenoid information, and all of that is on the other connectors that are on there. So actually, when you try to look at this differently than you do the MPU and look at it for what it really is very simple to read. They don't put all of the information on here that's on the MPU because some of it isn't necessary, but most of what you'll ever need for troubleshooting is right here on this page. And the more you study it, the more you learn about it, the easier it's going to be when the time comes. Let's go back to this MPU again for a while. We were talking before about a known good board and a hand-me board and a board out of a game. What I mean by that is we pretty much figured that this is the board up here out of the Knight Rider. We pretty much figured that this was all original. But if someone hands you a board, you've got to find out whether or not the guy's been throwing a bunch of chips in there that don't belong in there. I'm not talking about those stationary ones that are in every single MPU, but I'm talking about the personality ones. He might have thrown this one in out of an Evel Knievel and this one out of some other game, just to throw it in the parts bin. So you've got to look up these numbers that are on here and cross-check it with the list that we're going to give you for every single game made from Freedom on up to BMX. And you'll see those numbers in there are corresponding. Now that is part of the problem. After you've determined that yes, in fact, these are the right two personality chips, and yes, this is a corresponding number down here, then you've got to go ahead and check and see whether or not the right jumpers are in there. This is a jumper right here. And there's another jumper. So there's a list in there showing you jumpers, what jumpers belong on what game. Not every game is the same. The early ones are pretty much the same, but then after Lost World they started changing jumpers quite a bit. Now, if they've put the wrong chips in the wrong board with the wrong jumpers, you've got to correct all of that before you can expect this board or any board to work. And that could be all that's holding it up. It doesn't have to be anything wrong with the board at all. Someone's just gone ahead and either robbed an insignificant little resistor someplace because they needed it, or they've gone ahead and just thrown chips in. This could be a U2 and a U1 socket or vice versa. You've got to check that all out before you just write that thing off and throw it away. And a lot of times that's what happens, because they get these games ready to go in the back room of the warehouse, and they might just throw a board inside of it and not even be the board that belongs in the game, or it's been some board they started to do some work on and then quit. Anyway, this is a pretty simple layout, and I've elaborated on it for myself. I've got quite an extensive one with a switch matrix and a few other things, but if you simply want to power up a board and do some comparison voltage checks and stuff, this is really very simple. And all you have to do is scrap out an old game to get it. And you can do your troubleshooting at your leisure. You're not standing up inside of a cabinet trying to read a voltometer and trying to run over to another game and check the reading on that one. This way here, it's only a matter of a second or two between one board and the other. Okay, we're going to get off of this subject for a while and get on to something a little different. Now we're going to get into the transformer and power supply phase. What I've done is I've taken these schematics here and I've enlarged them so you can see them a little bit better, taking out some of the stuff that we don't need, and we'll be taking a look at this transformer circuit. Now obviously these windings don't really represent the true size, but what they are trying to do is show you primary and secondaries, how they're broken down. Your primary coming in over here on the left is made up of 120 volts, and then it's broken down into these different secondaries here. Let's start at the top. These are laid out pretty much the same way they are in the game schematics. You've got 43 volts DC through a bridge rectifier. Test point 5 should read around 43 volts. This one here at test point 2 reads 230 volts. I'll explain how that comes about. That's through a discrete component bridge rectifier. I'll explain that also. Next line down we got AC 7.3 volts. That's for your general illumination. That simply goes right on through the board and out the other side. It's just on there for a fuse. And test point 1 is 5.4 volts through a bridge rectifier. And down here at the bottom we have the 11.9, which we discussed before, test point 3. That goes through a bridge rectifier and on over to the voltage regulator. Now over here on the right, let's discuss quickly transformers. Get this out of the way. 3 different kinds. Isolation transformer, which would be the same amount of voltage on either side, 120 in, 120 out, which isn't used in a pinball game but is used in a video game to isolate the monitor so that the chassis isn't hot when you're in there working on it. So isolation transformer is pretty much strictly video game and TVs and that sort of thing. Next one is a step down transformer, a bigger winding on the primary than on the secondary. We got 3 of those here. And then there's one that's step up, 120 in and about 230 out. We're taking a smaller winding here and a larger winding and getting more voltage out of it. That's a step up. We're dealing with both of those kind. Now up here on the top, let's show how this works. Got 120 volts coming in on the line. It's called a sine wave. Starts out and crosses over the 0 voltage. 60 on this side, going back the other direction, 60, back up 60, 60. Peak to peak, you got 120 volts. And in the center, she drops back down to 0, but it averages out 120. Now, in the older games, they used AC on most everything that was in the game, and they didn't need to rectify it or change it to DC, but now they do, for lots of reasons. But let's just discuss quickly this rectifier business, because that's the most important part of this entire system. This is a blown up view of a symbol for the rectifier as it's in the circuit. This basically is what it looks like in a discrete form. You have an anode and a cathode. The banded end is always the positive end. Whenever you see one of these things in circuit, this end will be near the power source. Now what we're doing with this is we're forming what they call a bridge rectifier. There are 4 of these diodes, either in a package or in discrete, laid out on the board as 4 separate units. You come in with your sine wave on this side here. What you come with out on the other side is a clipped AC. You only have the top half. And it is unregulated, but it is DC. And in raw form like this, you can't use it for much of anything except the coils, because they can use a pulsating, I should say, DC voltage to its advantage. It doesn't really matter how clean it is. But if you're going to use this in any kind of regulation at all, it has to be filtered. So when we get into the solenoid driver board, I'll show you how they'll take this pulsating DC and smooth it out and clean it up and come up with a really nice straight 5 volts. Now down here on the right, it shows a couple of quick sketches here for physically what a rectifier could look like. On the early boards, they were very small, like this right here. They were only 10 amp. That's part of the problem with this we're going to discuss on the early boards. Later on they come out with a larger one, 25 amp. And this seemed to cure a lot of the problems. But on the early bridge rectifiers, with what we're going to deal with right now, these things have a tendency to blow out quite often. All it takes is just a quick short, and before this fuse, the slow blow fuse, has a chance to go, the bridge rectifier usually lets go. And they're soldered into the board, and they're quite a bit of work to get out. So we've come up with a couple of steps that we'll show you later on to eliminate the problem of a bridge rectifier that's rated too low and one that's too difficult to get in and out. Up here on top we discussed some fuses, slow blow, fast blow, two different styles. They're specified by SB and FB down here. The reason behind the slow blow is it has a spring coil element inside of it which will take a power surge when you initially start the game, or when it initially loads up a capacitor for the power supply. Rather than have that thing just blow out immediately, this will take a tiny power surge and still remain intact. The fast blows are meant for a slow, steady flow, and if you get a direct short, it'll take it right out. That's usually on your general illumination like you see here, and down here on the bottom on the 11.9 voltage is also a slow blow. A fast blow here is on your 5.4 DC voltage for your controlled lamps. Now, up here I've made a note on this 5 amp slow blow that's specified for the 43 volt. They made changes later on, and this was for a 2 flipper game. If you have a 3 flipper game or a 4 flipper game, that could change and the rating goes up. There's no special determination. At probably 6 amps if you got 3 and 7 amps if you got 4 is pretty close to right. But you can stand a larger fuse without any problem if you have more coils in there. Now what we're going to do now is bring over some rectifiers and show you the different kinds there are being used in these games. Well, this little one right here, you can put it in a clear space right there. That's the small one that you can find in, let me see if I can get in on that. Okay. A little focus wouldn't hurt. Alright. You find that this is the one that gives all the problems. The reason for that is it just isn't rated high enough. It's rated at 10 amps, and that's really borderline. So what they done on the later boards is to put a larger one in, which of course doesn't solve any problems on the early ones because they're not exchangeable. There's a much larger one. That's 25 amp. What we're going to show you how to do later on, though, is externally mount something that we can get from Radio Shack, rated at 25 amps. Nice heavy case, not too expensive. So anytime one of these little one here blows, we don't bother putting that same thing back in again. We'll show you how to remote wire one of these things and mount it on the inside of the back box. The reason for that is it just simply works better and lasts longer, and it's cheaper in the long run. Here's another configuration. These are found on Gottlieb games. We robbed them out of Gottlieb games and used them a lot. And the main reason behind using the larger bridge rectifier, of course, is to be able to withstand the power. Because after these components start wearing down a little bit, then the power becomes a problem, and the rectifiers start getting weaker and weaker. Now, especially on this one here, this is kind of important. This 5.4. This is for all of the control lamps, the ones that the computer controls. Later on, in other games, they also use this to run what they call a solenoid expander. And if this voltage here, this 5.4, drops down below a certain amount, as this thing weakens, then your solenoid expander no longer works, no longer pulls in, and you lose about half the coils that are inside the game. So anytime this thing here goes soft on us, I simply mount another one remote on there that's rated at 25 or 30 or 35 amps, and it cures that problem. is these simply just wear out after a while. Whether they short out or not, they simply wear out. Okay, what we're going to do now is set up a little fixture and show you just exactly what a bridge rectifier looks like, what it does, and how you can test one out. Alright, what I've tried to do here is lay this out as simply as possible so you can see. What I've done is connect 4 individual rectifiers. These are 4004s they're called. There's 4 of them soldered together. I deliberately shaped them like this so you can get an idea of the similarity between that and this right here. Now physically inside the package they aren't just 4 diodes laying loose in there, but basically that's what they're doing. And in actuality you could reproduce this bridge rectifier in the metal case with 4 individual ones. It's the same circuit. Your AC comes in on here on my bridge rectifier. It comes in here and here on this one. Your ground is on the bottom on mine, the DC out on the top. Same for this one here. Basically it's the same unit, but this package one of course is would certainly run a lot cooler, and it has its benefits. It will probably last much longer than this, because these are only rated at they're rated at less than an amp, and this is 25 amp. Okay, now before we discussed your volt ohm meter, I said you should try to find one, or you definitely should find one that has a diode check on it. Let me show you what a diode check is. You can see on the meter down here that they've got a diode painted right on there, and that's the setting that we're working with right now. That's a special setting on this. It's got nothing to do with an ohm meter in reality, because what you're doing is taking internal voltage and running it across this junction right here, and the measurement that you get will be the voltage drop across that junction. You lose some voltage going across a diode junction. So when you put your measurement on here, put the red lead right there, the black lead up here, you'll see her coming up with approximately, if I can get it to stay still long enough, a half a volt. Let me get a little better contact. There we are. Half a volt. That's a good junction on a diode. If you reverse the leads, it should be infinity. That is, no reading. It'll just stay on OL, which is overload, which is the same as no reading on this meter. Now here's an interesting little fact. If you start at this junction here and go on over to this one, it's the same reading as here. If you go up here at the top, you will find you'll get a double reading approximately, because you're reading across 2 junctions. So very quickly there should be no reading in this direction at all. I'm trying to get out of the way here. But there should be a reading in this direction. Now that's how you can check out the diode itself. You can check it out in circuit. So you put your red lead down here. I'll have to hold that one on there. That's reading a little less than a half a volt. That's okay. So this should read close to 9 up here. That's a good junction. Depends on the diode and its rating as to what you're going to read across the junction. Somewhere between 4/10 and 6/10, around a half a volt. You've got yourself a good diode, a good bridge rectifier. So that's basically what these bridge rectifiers look like if you lay them out as just discrete components. Now what we're going to do in the next phase is take a look at a transformer, which we might call typical out of a game that everybody has had a piece of. And we're going to find out what's wrong with it, check out rectifiers, discuss things like fuses, fuse holders, connectors, connections, what you can do about them, and pretty much everything you ever wanted to know about one of these power supplies. We're back and we got an old friend with us. You can remember this really tired looking transformer power supply that we had in the game originally. So we're going to use this thing as like a guinea pig to demonstrate some of the things that can go wrong with this and what you can do about it. Now mainly here, the interesting point is that even though the schematic, which we can get back here again, shows 1, 2, 3, 4 bridge rectifiers, in reality you only have 1, 2, 3. Well, the other one hasn't disappeared, it's just located down here in the corner in the form of 4 of those diodes, very much like the one I just showed you on that fixture a little while ago. Now they don't need a big heat sunk diode for this right here. This is your rectifying on your 230 volts for the displays. The reason why they can get by with these small ones is because it's very, very low amperage. Low amperage translates to low heat. Low heat means you can get by with this rectifying with these small ones. So later on in the newer boards we'll show you, they did it twice and they ended up with just 2 bridge rectifiers and 2 sections of these discrete components. They found they didn't need all of the bridge rectifiers. Well, let's just assume we got a problem with this one here, and you've blown out one of these little pukey little bridge rectifiers, and I dropped it down in there, and you're going to have to replace it. Well, I say don't. I say you throw that sucker away, because first of all it costs about $4. Secondly, it's going to burn out on you again. So how do you get around it? Very simple. We're going to flip this thing over so you can see what we've done. Move it down the line. Get off a little insulation paper here. Okay, what we've got here is 4 wires, 2 of them the same color. One, in this particular case, we just chose white and blue. Could be any opposite colors you want, a black and a white, a green and a white, doesn't matter. These 2 that are the same are obviously the AC going in the two corner pockets. They're marked out here as to where the AC is out here on the outside of the board, so you know which ones to put the AC in. Then the ground is on the bottom, that's white, and the power out is blue. You can choose any color you want. And then you just mount these out and you'd string them down like this, and you'd lay them perfectly flat and you'd tie them off so they'd be nice and neat, and you run them out to, in this case, one we stole out of a Gottlieb game, a bridge rectifier. This one is rated at 35 amps, even though it's not a heck of a lot bigger than the one that's in there originally. Now with this thing, you would take this and mount it externally on the side of the cabinet, wherever it's handy. Just run a screw into the wall. Now you've got yourself a nice rugged bridge rectifier that in case it ever did blow, which isn't likely anymore, you could change it in a matter of seconds because you're working outside. You don't have to take this panel off anymore. You don't have to mess around with these screws up here. You don't have to do anything once you've got this thing remote. So this is the way I solve the problem. I don't do them until they blow, but when they do blow out, I don't bother putting small ones back anymore. Now that even goes for the late ones. Let me discuss this late one. Okay, here is a late model power supply. 1980 on up, they began to use this one. Basically, it's the same unit. They've just put it on a board, laid it out a little different, gave it a little more room. See if we can get a little better focus on that. There you go. And they've also improved the connectors. They no longer have the pin connectors that they used to have, like this. They've gone to a Molex connector, or Molex, as you can see around here, on the outside. But if you look at the schematic for this one, it's almost identical to the early one. They've kept the numbers, the nomenclature, everything the same. The fuses, everything's the same. And you can see we got two sections of discrete components. Here's your high voltage one over here. It's marked high voltage section. Then over here on the left, get this cable out of the way, you got four more. Now that's your 11.9 voltage. They decided not to use a bridge rectifier. These are rated at 3 amp. These are pretty big. So this seemed to solve the problem. These are fairly easy to change. They're not expensive. And they didn't feel the need for any more than 2 bridge rectifiers. Right here, these two. But here's the problem with them. They got plenty of power. They're 25 amp. But if you can notice, if I can turn this just so, that the top 2 pins are not in alignment with the bottom 2. Well, that's so you can tell where the 5 volt is without, where the rather the DC outlet is, without marking it, although they usually are marked. You would put this in there with the offset pin as the 5 volt. All you need to, I tried it again, as the DC outlet. All you need to know is where the DC is coming out. The opposite end has got to be your ground. The other 2 are AC, and it doesn't matter which side you're hooked to which. So they have to have some means on here of identifying it. So they chose this particular one, which means this is the only one that's going to mount in this board. And these are expensive and hard to find, and only, you know, they're not in every single electronics store. However, you can walk into a Radio Shack and get the very same thing in this package. You can see those strong markings on there for positive and negative. These happen to be mounted in the center on each side, so these aren't offset in any way. So I would remote mount one of these like I showed you with the other one. If any one of these went, I wouldn't waste time putting these back in there again, because it just takes so much time to take this thing's got about 8 screws in it. It takes so much time to take this damn thing apart, remove all that solder, do all of that when this thing could be sitting right out here, remote mounted. Move over here. She could be down in here someplace. You just run a screw in there. Just run a self-tapping screw in there and put it in. Just run your wires right on over, either underneath the back of the board if you want, or right over from the top of the board. That's the solution for that. Now we're going to cover something else after I get rid of all this stuff here. This is something I think most of you will recognize because it's such a common problem. The Belle transformer, the early ones. Okay, I could lay it down like that, probably be just as good. Let that hang off the edge. There we go. Alright, this convoluted mess here, if I can show you what this guy's done. He's got all of these wires here, which weren't on there originally, of course, coming out from underneath the back. He soldered them on there. We're going to have to clean all of that up and remove it. And why did he do that? Well, he did that because you can spot it now. There's a missing pin right there. This is burnt. This one's fried. Down here in the bottom, there's 2 of them fried. That's usually your GI. And the reason for that is they expected, Belle did anyway, when they first designed this, they expected this little tiny connector here, if I can hold on to it with my fingers, is going to rest on top of there and carry all of that amperage required for the lights. You can see that it only makes contact on one side, on that connector, the flat side. So you get that pin coming out there in a very, very small amount of surface. So of course that's the weakest point in the entire system, and that's the part that's going to arc over and start to burn. It'll get so hot it'll actually burn the plastic, like it's done right here. Now they tried it, what they figured it was a cure, and they come out with this fancy schmancy one here, which has got, difficult to see, but you can see, if I hold my finger behind it there, it's got sides sticking up, ears sticking up on the sides. So when you insert that one in there, Now you got 3 sides working for you instead of the 1. I don't know how difficult that is to pick up, but basically that's what they did. But again, that only temporarily solved the problem. Now the only cure, or the factory cure, that the only one that they recognize is that you're going to take this header out of here, desolder it, put a new header in, and start in all over again with the same old problem. You'll have to change the connector. This is the male connector here. You'd have to change the female connector on the wiring harness, because that's going to be burnt just as bad as this down here. And all of that just delays the problem until the next time around, because it's going to do it again. So I've come up with another solution I like a little better. And we will get into it shortly. I'll have to do a lot of setup and everything else. Let me show you what this guy's done. If I can turn this thing over. He's tried to solve the problem by going in the back, turn it like so, and he's mounted his connections onto the back of the pin, figuring that is more area than that pin was and that clip was before. There's one that just fell right off. That's the reason why this don't work too good. And he did that with 3 or 4 of these. He didn't even bother to color code them, so I guess he must just remember each time he goes to work on it, because he had to have some kind of a disconnect to be able to remove the harness out of the game. So this was his solution. He was on the right path, but he didn't go the right direction. And there really isn't enough area here, because you can take these things and pull them around. They'll come right off of there, because that pin still isn't big enough area. I'll cut those out of there later, but right now they look like they want to fall out of there. This one here does anyway. So this is not the way to fly. What we're going to do is, I'll explain to you first what we're going to do, and then we'll go ahead and do it and show you how it's done. We're going to find an area on there that has plenty of material for us to mount some wires. We are going to put a remote plug on there. We're going to completely forget about this connector right here. We're going to give the game a new connector. And it's going to be one of these. More pins than this, but this is the general idea. And this comes from Radio Shack. And the reason why this is a better system is right here. Here's a male and female connector, like they ended up using in the 80 and later games. You got 360 degree surface of contact here. And that's a lot better, even though gauge wise it's about the same. That's a lot better than the original system. This won't give you a problem. And if you thought you had a problem, you could run additional wires to carry the extra load. The more wires, the more load you can carry. So this is what we're going to be working with. And what we're going to do is find ourselves some good spots on here. There's some excellent spots up here near the test points. Get this thing moved down a little. Trying to get rid of that light. Up here near the test points, we can scrape off an area and get about a half a square inch of raw copper material. Or we could find some other place on here. I like it up along the top right here because it's more convenient. It's near the test points. You're out of the way of everything else. You can run the wires up and over out of the way. Now this is another set of wires in addition to running the remotes for the bridge rectifier. So it can get look kind of wild after a while. But the bridge rectifier ones you can run over in back of the board off to one side. The ones for the connector repair you can run up off this direction, which is the way they'd go anyway. Now, the one you have the problem with mostly, the burnt one here, is the general illumination in and out. There's usually 2 pins in, 2 pins out. This one goes to the play field, so this entire connector is going to just sit right there. We won't bother it, we won't cut it out, we'll leave it there. We'll be doing a repair on that, but while we're at it, we're going to pick up on these 2 down here. So it's going to have 2 separate connectors, because this one goes to the playfield. If you ever wanted to take the playfield out of the game, you wouldn't be able to remove it if you tied it in with this one over here. So you need a 2-pin connector to take care of this one here in the center, and probably a 6-pin connector to take care of this one over here. So that's the next step, and I'll probably go ahead and partially complete it, and then get back and show you what we've done, and then go ahead and finish it up and show you how nice and neat it comes out. Give us a little while for setup. Alright, I've gone ahead and done the work on the transformer. I'll show you what we did. First of all, we had a problem with one of the bridge rectifiers, so I remoted one. As you can see, the new solder up there on the first bridge rectifier. And there's the finished piece right there. That'll be mounted to the inside of the cabinet. That's done not as a ground as much at all, actually. It's done for heat transfer. You mount it on the sheet metal and it'll keep it nice and cool. Now, I got two connectors coming off of the board up here. The reason for that is this one was so bad we had to do two of them. And the one that I told you I was going to eliminate was this one right here, because the burnt pins, missing pins. That's this one right here with 6 pin connector from Radio Shack. Now looking at the colors, you've got a white and green, which is ground for AC, a red and an orange, which is the high side of AC, a brown, which is your 43 volts for the coils on the playfield, and a blue, which is the controlled lamp bus. So that's the 6 pieces that we took off of here. So that's mute right now. That's just sitting in there and it's going to remain there. We could cut it out, but it really doesn't make any difference. And that one will be on its own separate connector. Now the other one, coming off of the same junctions, we're sharing the same pads up here that we picked up these voltages from. I'll get up closer on that in a minute. Here's a 4-pin. This one is strictly AC. You got 2 grounds, a white and a green, 2 hot sides, a red and an orange. Now, we needed that one because down here in the center we got 2 really bad burned pins, and over here to the left we got 1 burnt one and 1 missing one. So the AC going to the back box, that's where this connector goes, just to the back box. The AC to the back box was heating up and burnt these, pulled them right out of the solder. So rather than mess around, what we'll do is now we'll put the connector back on there after we remove just the 4 wires. There'll be a red and an orange and a white and a green. We'll take them out of this connector. The rest of them are running cool enough to leave them alone. And those 4 will be the other half of this connector that'll allow you to take this bottom connector off. That's the reason for 2. Okay, this one here, for the bottom row. The one with 6 pins took the place of this connector right here. Now this is extreme, and maybe you don't want to get into this, but if you're going to go ahead and do all of the work to take this header out of here and replace it, and then clean up and put a new connector on the other end that comes from the playfield, do the same thing for this bottom one that goes to the back box, you're going to spend twice as much time and twice as much money and still end up with the same problem. This connector won't burn. It's got enough area to conduct that simply just won't burn. At least they haven't for 8 or 9 years that I've been doing them. Now let me come in on this top row here and see if we can come in on that and see if it wants to focus. Wants to focus back where we were. That's okay, I'll settle for that. Now up here on top, I pull these wires out of the way. You'll see what I've done. This bright area right here, we scraped off the film that they use, the green film they use for printing. We scraped it off, and this is where we picked up our 6.5 volts for the blue wire. One down here, and we got 4 connectors, 2 wires going in one direction, 2 wires in another direction, 4 on this hot side on the AC. 1 over here, brown, on this connector. These are all right next to the test points, and the test points are still there. You can still get your probe in there for the test points. This is your 43 volts for the coils. Now you come down here, and we stripped it off right next to this power resistor, this high wattage resistor. We scraped the sideboard off. We ran 2 wires up in the air to go in this direction, and 2 wires down to go in this direction. The same 2 colors. You got green and white going up off the top for this connector. You got green and white coming off the bottom for this connector. We just scraped a long pad there and connected 2 wires on one end and 2 on the other. That's a little easier than trying to put all 4 of them together and lump them up. Now while we're at it, this is where you should put your connector underneath here when you're doing any DC testing, on this board. You want to check out these DC voltages. This is real handy. Don't just put the probe in there, because I guarantee you the probe will come over and ground out this 43 volts and blow that rectifier across the room. So what you want is to use an insulated alligator clip right underneath there where it joins on, and you get yourself a really good contact, and then you can go do your DC checks up here to see if your voltages are alright. When you do an AC check, you can use that same ground pad that we showed you, and you can just simply change the meter over to AC to pick up to make sure your AC voltages are up. Now let's do something on fuses. We touched on it before, but I wanted to show you. I'm sure you're all familiar with fuses, but let's go over it one more time. This one here with the little I-beam inside of it, narrowed in the center, that of course is your fast blow. If I can get the light off of it. There it is. That's a fast blow. Now normally, slow blow looks like this. At least the ones I've been using do. We can get a picture of that. It's got a little coil of wire inside of it, and then a thin wire at the other end. Now there's another type of fast blow, slow blow. Slow blow. Alright, show you what they look like. It's just a wire wound, difficult to focus, it's so small. It's just a wire wound, one continuous wire winding, thin wire, over a piece of ceramic or something in the center. These ain't worth a damn, but this is what you're going to find that most houses sell to you, because this seems to be the cheap way to produce a so-called slow blow. But if you can find them, this is the one you want. This will take the pulses over and over again without blowing. That other one won't last anywhere near as long as this one here. But these aren't that easy to find, now that they're all pumping out those other ones anyway. Alright, something else. Whenever you're taking these fuses out of here, and invest a couple of bucks, get yourself one of these for taking the fuses out. It's an automotive tool, or it's an electronic tool, whatever. And it just does a nice job. Easy way to handle them. When we got it out of there, I'm going to show you something else. It's very possible that this fuse can be in here, making good contact on this top clip and none at all on the bottom, if they haven't been bent in recently, or shaped or formed. So, anytime you take a fuse out, you want to go in there, put some tension back on those, and you'll make sure that you aren't suspending that fuse in midair and making a bad contact down here on the bottom. Now, let me show you something else that I hooked up that works out really nice. I'm going to take this fuse out of here. Suppose you're having a problem with that particular circuit. It seems to be blowing fuses. Well, that particular one there is a fast blow, which are kind of cheap. They're about 30 cents. These slow blows are getting up to being close to $1 a piece. If you're buying volume, they're about 60, 70 cents. So if you pop about 8 or 9 of those before you find out what's wrong with the board, you've spent a lot of money. What I've got here is an inexpensive circuit breaker from Radio Shack. Thank God for Radio Shack. This is a 2 amp, but it doesn't matter whether it's 2 amp or 1 amp or 4 amp, because if you've got a short, it's going to pop this thing open anyway. So I insert this, you can see where I soldered some pieces of copper tubing on there, a round stock or a bolt, anything you want. Left a gap in the center, of course, so we got no circuit. I'll pop that in. Now I'll go ahead and work on the circuit, and I'll press this to set it, and you'll hear that thing snap whenever you got a short or beyond the 2 amps. And this is really nice because you can pop this thing all day long and not spend any money. If you start loading this thing up with fuses, you're going to run out of the fuses that you need later on, and you're going to wish you hadn't. So this is nice. Just take the time to put one of these things together. Maybe it costs you $2-3 when you get done. Save you a lot of grief. I'll pop that fuse back in there. So we just about covered everything there is, I think anyway, on this transformer and power supply. And we'll touch a little on the new one later on when we get into working on some other stuff, but the new one actually is a clone of this one here. It's just shaped a little different, looks a little different, but it's basically the same. Principle's the same. So I think we'll get set up now and we'll see if we can get something else set up here. Probably lamp drivers I think we'll get into next. Okay, finally we can talk about something that doesn't break, or at least not very often anyway. This is an early style lamp driver board, and you can see it's pretty dense. It's kind of tough to work on because of the fact that it's got so many traces jammed in. Plus you got an extra row of ICs here that the late board doesn't have. So this is okay board to use. They're both exactly the same as far as use is concerned, but they got rid of this one after a few games and went for different style, and this is it here. As you can see, it's less cluttered and fewer ICs. Same number of SCRs though, as silicon controlled rectifier. This is what drives your bulbs on the playfield. So you can see that this one here would be kind of tough to test compared to this one. But fortunately, you don't have to do much of anything on these. I'll show you a couple of tricks. There's only 3 connectors you're concerned with here. This one up here on the left is your power in and the code to tell which lamp to turn on. These are all returns right here. This happens to be the back box. This is playfield, playfield. Alright? Let's just say you got a lamp out on a playfield. And the first thing to do is to take out a bulb on an adjacent one. You're in lamp test now, I assume. Take a bulb out on an adjacent light and try it. If that bulb is good in one socket and not good in the one that you're working on, then probably you got a return problem. The next thing is to make a note of the color. We'll say it's a white wire with a red trace. You don't even need a schematic for this. You'll come back down here and you'll only look at this connector and this connector because these are playfield. So you're down to just those two. This one over here would be the back box. So you find yourself a white and red wire. And unless they're being silly, they'll only use it once. They might use it twice, but a lot of the times they got enough color combinations they only use it once. Now we'll say it's the bottom one down here and this one right here. Alright? You're going to get yourself a test lead and put a paper clip down inside the connector. Connector's on. Put a paper clip inside there. Alligator clip on the paper clip. Take the other end of the alligator clip and go over to any ground trace inside the game and touch it. That light should come on. If it doesn't, then you've got a continuity problem, a wiring problem going from here back to the playfield. If the light comes on, then probably it's the SCR associated with that pin. Let's just say it's this one right here, for convenience sake. It probably is anyway. Now the next test is to get yourself a small screwdriver and you're going to insert this small screwdriver in these 2 leads right here, right across those 2 leads. You're going to touch both of them with a small straight screwdriver. In effect, what you're doing is turning on this SCI here mechanically by just connecting these 2 leads together. This is a switch, nothing more, nothing less. The lead in the back of it turns the switch on, connects this lead with that lead. That's it. So you're going to do that with a screwdriver. Now if the light comes on, now you know you're good to here, you're good through the trace, you're good to the SCR, replace the SCR. It's as simple as that. You can do the same thing with these larger ones. The reasons why they have these larger ones here, on some games, they drive 2 lamps. They'll drive a player shoots again, might have 2 lamps in the back box, or one on the playfield and one in the back box, whatever. You might want to drive more than 1 lamp. So this is simply a larger version, more amperage, of the small one over here. either one of them can go, but they don't go very often. You accidentally short out a bulb inside underneath the playfield. That's usually what makes them go, because they're pretty rugged. Now, where you can run into a unusual problem with this is if you've had battery acid damage on an MPU and it's been there for a long while, it can now drip down and start down on this board right here. I've got 3 or 4 of them that have been ruined. They aren't worth spending the time to clean up all the copper traces, all these SCRs, all these resistors. It just isn't worth it. There's so many of these lamp driver boards out there, it's simply easier to just use that one for spare parts. You just omit the area that's been damaged and you just rob SCRs out of it and occasionally an IC. I've never replaced one of these ever in 10 years. So this whole system, because it's operating at such incredibly low voltage and amperage, it's very reliable. You really got to go out of your way to do any kind of damage to it. Now they also have what they call auxiliary lamp driver boards. They come in 2 different sizes, 2 different styles. And what they're doing with that is they're making up for the fact that they can't run enough lights with one. And not too many games have got them. The later games do. The 81 games, the ones with lots of light in the back box and lots of extra lights on the playfield and xenon with a tube and all of that stuff. So what they did was make up a couple of small boards. I'm going to find you a picture of one or both of them. And in effect, all it is a miniature version of the very same thing that we're working on right now. And here's a shot of one right here. This is called A9 Auxiliary Lamp Driver. This one here has got approximately, let me see how many it's got here. 28 SCRs. So this can drive an additional 28. They have a smaller version that drives to 12 or 15. Depending on which one they need, that's the one they use in the game. But again, it's tested out exactly the same as this board here.